All right, so today is a pretty exciting day because today I'm going to tell you about the principle of least action. All right, what is the principle of least action? Well, say you have, a uniform gravitational field with some gravitational acceleration g, where g, is your regular 9.8 meters per second squared. And say you have a ball and you throw the ball and it goes in some trajectory, right? Well, at every point along this trajectory, the ball has a little velocity, right? And it also has a height. So we can define a quantity, and I'm not saying why I'm defining it yet, but we can define a quantity, L, equal to 1/2 m, where m is the mass of the ball, times v squared minus mgh. So notice that what I've defined right here is the kinetic energy of the ball minus the potential energy. And it's not plus the potential energy. If it was the kinetic energy plus the potential energy, that would be the total energy of the ball. But instead it's minus the potential energy. And that's kind of weird. But all right, so you say, okay, well, you can define this thing L. I'm saying, okay, wait. Let's say the ball at the starting time that we threw the ball, the time that we threw the ball is t1. And when we stop, thinking about the ball, we're going to call that t2. So the start of the trajectory is at the time t1. The end is at the time t2. So we can define another quantity, s, which is equal to the integral from t1 to t2 of L dt. And this is just the integral of L at every time between t1 and t2. And L, you could think of it, if you like, as like a function of t, because at every different time, the ball has a different value of L. But usually people don't write that. So I'm not going to write it, but you could. All right, so okay, I've defined L and I've defined S. Well, what's the point? All right. Well, there are a lot of different paths, you could imagine that this ball would take. I mean, it only actually takes one path, but, you could imagine that the ball went like that, or, let's see, you could imagine that the ball, I don't know, something really crazy, like the ball would travel in some like really weird trajectory like that. But travels in a very reasonable trajectory. It travels in this parabola. And what I am claiming, let me get my, well, all right. I'll use my orange now. Claim. The path that the ball really takes is the path that minimizes S. So this is the principle of least action. S is oftentimes called our action, and L is called our Lagrangian. And these are just names, but, why is it called the action? Well, it's not really that good a name. It's just like it seems like such an arbitrary quantity, right? The kinetic energy minus the potential energy. Like, it doesn't really have anything to do with like action in the way you think about it. And Lagrangian, well, it's just named after some guy named Lagrange. But it's kind of weird. Like, you define this weird quantity, and the path that the ball really takes in real life is the path with the smallest possible action, because each of these paths has some sort of action that we could calculate. But apparently, the parabola has the smallest action. And this kind of makes sense if you think about it. So let me just say like why it makes sense. Like let me draw this again. So we have to specify a start time and an end time. That's really important. We have to specify where the ball starts at what time and where the ball ends at another time. And we're only considering the paths that start at the same point and end at the same point at the same times. So if we want, let's say we were trying to figure out like what path minimized s, and we wanted s to be small, right? Where, as you remember, s is the integral from t1 to t2 of L dt. So in general, if we want s to be small, and by small, I don't mean like close to 0, I mean like really as negative as possible. Or it could be positive or negative, it doesn't really matter. But, I don't know, what's a good word? S to be least. Yeah, let's say that. Let's say we want S, well, we want S to be, I guess I'll say we want S to be minimized. If we want S to be minimized, then in general, we want L to be minimized. And L isn't a constant over the path, right? The kinetic energy plus the potential energy is a constant. But L, which is the kinetic energy minus the potential energy, isn't a constant. So sometimes it might want L to be a bit bigger or smaller at different times. But in general, we want to minimize L, right? And L, as we remember, is 1/2 mv squared minus mgh. So if we want to minimize L, right? If we want to minimize L, then in general, well, because of this term, we want V to be minimized. Whoops. V minimized. And we want H to be maximized. So here, that's because of this term. That's because we're subtracting off H, right? Because M and G are positive. So in order for L to be minimized, we want V to be minimized, but we want H to be maximized in general. So if we look at the true path of the ball, we can kind of see that, right? Because these interests that we want V to be minimized and H to be maximized are two competing interests. Because we want the ball to be really, high up. We want it to have a large height. But we don't want it to travel too quickly. So there are these competing interests. So in general, the path, well, not in general, it is true that the path that the ball takes kind of negotiates these competing interests, right? It wants to be high up, but it doesn't want to get there too quickly. So it kind of has to, get to a large height, but also take its time. So it turns out that this doesn't only work for a ball in a gravitational field. It works for any potential energy. V not just, or V, we could have a potential energy V that's not just mgh, right? And I'm going to show you that let me even put this in, or let me use blue. I will show that the principle of least action is completely equivalent to Newton's formulation of mechanics, of F equals ma. All right? So I made some pretty bold claims so far, and now I have to start the interesting process of actually proving my bold claim. All right, so I'm going to start this off by just doing the one-dimensional case. So x is the position of a particle, and x dot is the velocity. So x dot is just dx over dt, and that's just notation. So once again, our Lagrangian written in this notation is 1/2 m x dot squared minus v of x, where v of x is the potential energy of our particle at position x. I'm going to also introduce a bit of notation. I'm going to say that our action is a function of our path. And this is not too crazy. I'm just saying that the action depends on what path we take. So that's all that means. All right, so how do we actually find which x of t? So x of t is a function of t, right? How do we find which x of t minimizes s? It seems as though, you have to try out all the millions of paths, right? How do you find how do you try out a million paths and calculate the action for each path? Really, there's an infinite number of paths, right? So how do you do it? Well, there's a few tricks you got to do. They're not really tricks, but we got to think about the problem a little bit differently. So let's start doing that. So here we're going to graph x as a function of t, and we're going to specify start and end points to all of our paths. So remember, this is just in one dimension. So this is time here. All right. So we're going to say that our path starts at x1 at time 1, and it ends up at x2 at t2. And how do we find the path that minimizes the action? Well, first off, let's say we knew which path minimized the action, right? Let's call this path x bar of t. And x bar, this is just notation. The bar is just notation. X bar of t is the path that minimizes the action. Now, here's the important part. Every other path that you could take, all the other paths, which will just any given path x of t is equal to x bar of t plus eta of t. Eta is a Greek letter. It kind of looks like an N. And we have to say that eta of t1 equals 0 and eta of t2 equals 0. And this is so that x of t1 equals x bar of t1, which equals x1, and x of t2 equals x bar of t2 equals x2. So we want all of our paths to start at x1 at t1 and end at x2 at t2. And every path can be written as x bar plus eta, as long as eta of t1 equals 0 and eta of t2 equals 0. All right, so we haven't done anything. All we've said is that every path can be written as the true path plus eta. All right? Now, here's the next thing you have to realize. Every path can also be written as x bar of t plus some constant epsilon times eta of t. So here epsilon, another Greek letter, is a constant, and eta is still our same old function of t. Right? Now, this is just another path. I still haven't done anything. But the point is that if we choose, let's say we decide on an eta, right? We say, okay, we're going to have this eta. If we choose different epsilons, we get different paths. Now, here's I guess the important part, right? S, well, S of x bar of t, right, is always going to be less than S of x bar of t plus, well, epsilon times eta of t. And that's just how we defined x bar of t. X bar of t is the path that minimizes S. So this isn't really even saying anything. So S of x bar of t is always going to be less than x bar plus epsilon times eta. So if we want to, as long as we choose our function eta beforehand, we can, well, I didn't actually mean to do that. As long as we choose our function eta beforehand, we can think of this as just a function of epsilon, right? Where we have just written above that if epsilon is 0, you always have less than epsilon is non-zero. Well, this is like mixing up notation a bit. But the point here is that we can think of this whole thing. We can think of this whole thing as just a function of epsilon, as long as we fix eta beforehand. All right, so here is really, in fact, I'm going to write this really big. All right. So from just like regular old calculus, we know that, well, I'll use different colors to make it dramatic. We know that the derivative of this expression we know that if we differentiate the action of this path, x bar plus x bar of S of x bar plus epsilon times eta, and we differentiate this with respect to epsilon, fixing eta, and we evaluate at epsilon equals 0, this is 0. And that's because x bar minimizes S. And this is like the key sort of thing that's going to really allow us to figure everything out. Right? This is like the key thing to realize. When epsilon is 0, we have the minimum possible action. And when epsilon is not equal to 0, we have some different path. So this is true for all eta of t, as long as, eta of t1 equals eta of t2 equals 0. All right, now I'm going to write this in a form that is more familiar to physicists. And it's going to be the same thing. I'm going to delete this thing right here just to make space, but it's still true. All right, what is S of x bar of t plus epsilon times eta of t? This is just equal. This is just from a regular old calculus knowledge of, equal to S of x bar of t plus a term that I'm going to call delta S. I'll tell you what this is in a second. Don't worry. Plus something I'm going to call O of epsilon squared. All right. So what did I just do? I just defined a bunch of notation that might look a bit familiar to other physicists. But what is this? This is just equal to epsilon times d epsilon of S of x bar of t plus epsilon times eta of t evaluated at epsilon equals 0. So all I did here is I said, all right, this right here is a function of eta, assuming we just decide on, sorry. This right here is a function of epsilon, assuming that we fix eta beforehand, right? This right here is a function of epsilon. So I'm expanding it. First I'm saying, okay, what's this really saying? I'm saying f of, x plus epsilon is equal to f of x plus epsilon times the derivative of f of x plus higher order terms. This is really all I'm saying with this whole equation here. This right here is just epsilon times, the derivative of this function with respect to epsilon evaluated at 0, plus higher order terms of epsilon squared, epsilon cubed, epsilon to the 4th. All those terms are in what I'm just calling O for order, O of epsilon squared. All right. So what I really did here is I just made a Taylor expansion. Of my function around epsilon equals 0. And what I want to say is that this condition right here that I started with, well, clearly this condition is the same as just saying delta S equals 0. But what it means is that when we're computing when we're actually computing this, what I'm saying is when we compute this function, right, we can expand it in powers of epsilon. And first we'll have a term without epsilon. That's just the regular old action where epsilon is 0. And then we'll have terms where we have epsilon to the first order. And then we'll have terms where we have epsilon to a higher order. We can just throw out these terms. And why can we throw out these terms? Well, it's just because we made a Taylor expansion. I was going to say something complicated. There's nothing complicated about it. All right? So this is sort of going to be how we actually go about, figuring out this thing. And now I've made a mess. I've written a bunch of stuff on here. But we're going to expand this out. We're going to expand this out in powers of epsilon. And we're only going to keep powers to the first order in epsilon, because that's all we need in order to satisfy this equation, this equation. And we're going to write this as saying delta S equals 0. All right? Just a lot of notation. All right, I'm sure you're ready for me to really get to, showing that the principle of least action is the same as Newton's laws. But I just want to say one more thing about this. I know I just want to write it out again so I can just get a clean board. I just want to say one more thing about this. S of x bar of t plus delta S. What color did I use here? I think it was that one. All right, so once again, S of x bar of t plus epsilon times eta of t equals S of x bar of t plus delta S plus terms of order epsilon squared. All right? Now, this is just a fact of small numbers. We can always find an epsilon small enough such that, or let me stick to my colors that I decided on. O of epsilon squared is a lot smaller than delta S. All right, and that's just because delta S is the first order in epsilon, whereas O of epsilon squared is the second order. So we can just always find an epsilon really small such that this is true. Whoops. So this is true. And this is really why this allows us to maximize our path. So imagine there was some eta of t such that delta S wasn't equal to 0, right? We said our path is maximum when delta S is equal to 0. I want to really investigate that claim. So I'm saying imagine there was an eta of t such that delta S wasn't equal to 0. And remember that delta S depends on fixing an eta. So depends on fixing an eta of t beforehand, right? Well, what would that mean? That would mean that S of x bar plus epsilon times eta of t was equal to S of x bar of t plus something that wasn't 0, right? So if delta of S was bigger than 0, or rather, let me actually start the other way. If delta of S was smaller than 0, then we would have a path with a smaller action, right? Because I'm saying we're using an epsilon so small that this term doesn't matter. So if delta of S is less than, if delta S was less than 0, then we would have a path with a smaller action. Namely, it would just be the path x bar of t plus epsilon times eta of t, right? Because this function would be, well, this number would be this number plus a negative number. So this would be smaller than this. So we would have a smaller path, so we have a path with a smaller action. So what if, we also deal with the other case, right? If delta S was greater than 0, then we would still have a path with a smaller action. And that path would just be x bar of t minus epsilon times eta of t, right? Because there's a whole epsilon multiplying this term. But it doesn't matter whether delta S is less than or 0 or bigger than 0, right? Because either way, we can still find a path with a smaller action. That's why we require that this term has to be 0 in order for this to truly be the path that minimizes the action. All right? It's just thinking about regular calculus, but I wanted to stop and just say that because it's important to refresh yourself every so often. All right, so we've done all our thinking, and now we're finally ready to do some actual math. Well, I guess what we actually had was math, but it was really more like thinking. There are a lot of cool ideas, but now we're finally ready to actually do something. All right, so S of x bar of t plus epsilon times eta of t equals the integral from t1 to t2 of 1/2 m whoops, oh yeah, times x bar of t, dotting that, plus epsilon times eta of t, dotting that, squared. Okay, so this whole thing, this is just x dot, where, you know, this is like x. So we're just taking this, we're dotting it. This is just 1/2 mv squared, if you remember. Now, all of this minus v of x bar of t plus epsilon times eta of t. And then, never forget, all of this times dt. Never forget the dt. So, we just plugged in our path into our definition of the action, right? And now we have to go about expanding it. And the whole point is that we're only going to keep this to the first power in epsilon. We're not going to keep it to any higher powers. So let me start my next line here because it's probably going to be a very long line. So this is all equal to the integral from t1 to t2 of 1/2 m. And now I have to expand out like this squared, right? I'm just going to expand out the squared. That's actually all I'm going to do in this step. All I'm going to do is just expand out my square. So x bar dot of t squared plus 2 times x bar of t dot times epsilon times eta of t dot, right? That's our cross term. And then the last term plus epsilon squared eta dot of t squared. All right, all I did was I expanded out that squared. Let me actually draw that a little bit cleaner. Yeah, and remember, we're only going to keep stuff to order epsilon. We're not going to keep stuff to order epsilon squared. So I'm going to cross out this term, epsilon squared times eta dot squared. All right, what's the next term? Well, we want to write out this, but only to the first order in epsilon. So minus v of x bar of t, and then we have minus epsilon times eta of t times v prime, where prime, I just mean the derivative of v, oops, v prime of x bar of t. And now all of this dt. And so you might be wondering, like, wait, how did we get from this part to this part? Well, it's the same exact thing as just in regular Taylor expansion. F of x plus, epsilon with some tiny epsilon, or is about equal to f of x plus epsilon times f prime of x, right? Where f and x are just not the same x. But this is just like, a linear approximation in f. And we're only concerned with keeping stuff to the first order in epsilon. So that's all we're worried about. Whoops, still a little bit there. All right. So that was pretty exciting. Let's rearrange this a bit. So this is all equal to the integral from t1 to t2 of 1/2 m x bar of t dot squared minus v of x bar of t. So right now, I just took this term and I took this term. I put them here, right? And actually, I'm going to write dt here. You'll see why I'm doing this in a second. And then I'm going to say plus, once again, the integral from t1 to t2 of, okay, so you see here we have this 2, and here we have this 1/2, right? So those cancel out. So the integral from t1 to t2 of m x bar of t dot times epsilon times eta of t dot. All right, so that was this term right here. Actually, that color doesn't look good enough. That was, I don't know, what about gray? That was this term right here. Guess what the next term I'm going to write is? Minus epsilon times eta of t times v prime of x bar of t. Well, I almost ran out of space again, but I just have enough. Whoops. Oh. Yeah, and I have to put this all in brackets. Okay. Whew. So why did I... Oh yeah, and as you can clearly see, that is just this term right here. So why did I rearrange it like this? Well, that's because, as you can see, this term right here is just our original s of x bar of t, right? And then this term right here, we can take out the epsilon, right? Right, plus epsilon, because see, we have an epsilon here and an epsilon here, and we can just take both of those out into the front of the integral. Plus epsilon times the integral from t1 to t2 of m x bar of t dot times eta of t minus eta of t v, v prime of x bar of t, and then never forget dt. Whew. So we successfully expanded out. I mean, it's kind of tiring. But it's very cool. It's tiring, but it's cool. We successfully expanded out the action of x bar plus epsilon times eta into s of x bar plus epsilon times some other thing. So we successfully expanded it out to the first order in epsilon. So this whole thing is what I was earlier calling delta of s. And I'm only calling it delta of s because that's what a lot of physicists call it, and you might read something else. But yeah. Okay, so we're not done yet, but we've done actually a lot of cool stuff. We only have like a few it's all actually been pretty cool, right? We only have a few cool things left to do before we finish. So hang on tight. Okay, actually there's a mistake in here. This should have a dot. A lot of you probably noticed that, but there should be a dot right here because there is a dot here, so there should be a dot right there. All right, sorry about that. A lot of you probably noticed that. Hope you noticed it. Okay, so let's rewrite this all a bit. Just clear this stuff out. All right, so if you recall, we wanted to have delta S to be 0, right? We want delta S to be 0. So we're just going to take all of this and we're going to move it right here. And we're going to continue to clean up a little bit more. Get rid of that. Get rid of that. Get rid of all that. Okay. So, the next thing we have to do is, and you'll see why we have to do this, but right now, I'm just going to do it, and then we'll see why I did it, is we have to integrate by parts. So, how does integrating by parts work again? So, I'm just going to sketch out for you really quickly. So, the product rule in calculus, if you have two functions, f and g, right? And you differentiate with respect to f and g, that's equal to f dot times g plus f times g dot. All right? So we could rearrange this to say f dot times g equals f times g all dotted minus f g dot. And then we could integrate both sides. We could integrate both sides. Whoops. And then, by the fundamental theorem of calculus, this whole thing, well, I guess we have to integrate. I guess I should put some bounds on my integral. We integrate from t1 to t2 and all these integrals. t1 to t2. And by the fundamental theorem of calculus, this is just equal to fg evaluated at t1 and t2. And by that I mean you evaluate at t1 and then you subtract off evaluating at t2, as I hope you know. Minus, I'm just going to rewrite this term again, t1, t2, dt, fg dot. All right, so integrating by parts, what do? We want to solve an integral like this, right? Where we have a derivative on one term. We can first write this term where we just have f and g evaluated at t1 and t2, and then subtract off the integral where this is how I kind of think about it. I kind of think of like switching the dot from f to g, and we also have to make sure we have a minus sign here. So that's how integration by parts works. And actually, maybe I'll rewrite it here kind of neatly. T1, let's write it here. F dot g dt. I'm going against my color coding a little bit, but that's all right. Hope you can follow anyway. So the integral from t1 to t2 of f dot times g dt equals f times g evaluated at t1 and t2 minus the integral from t1 to t2 of f times g dot dt. All right, so that's integration by parts. Now, using that, I'm going to rewrite my expression above. So first off, the epsilon just stays out front. And what I want to integrate by parts is this thing right here. So the first thing I have is epsilon times m x bar of t dot times eta of t. So in other words, okay, let me just finish the process before I start talking again. Evaluated at t1 and t2 minus the integral, I guess I still need the epsilon up front, minus the integral from t1 to t2 of m x bar dot dot of t times eta of t dt minus epsilon times the integral from t1 to t2 of eta of t times v prime of x bar of t dt. All right, so let me just talk for a second about what I did. Okay, this term I just put here. I didn't do anything. All right, I didn't change anything about that term. This term, this term I integrated by parts here and here. So I took I guess I took this to be f dot. Let me write that a little better. I took this to be f dot, and I took this to be g. So then g came here, f dot, or just f was here, and then here was g dot, and then here was f. So I just integrated by parts. Okay, let's undo all that. Okay, and now that I have successfully integrated by parts, I am now going to get rid of this because I just did it. Boom. All right, so here's the important thing. This was from a long time ago. I hope you remember it. But we had to have eta of t1 equal to 0 and eta of t2 equal to 0. And the whole point was that our path that was that every path can be expressed, as x bar plus epsilon times eta, but eta has to be 0 at t1 and t2. So this whole thing that I spent so much time writing out is actually just 0 minus 0 because of this eta of t right here. So this whole thing I can just cross out because it's all 0. Now, so this all equals negative epsilon times the integral from t1 to t2. Okay, we're really getting close. It's actually very exciting. Times eta of t, and then all in brackets, m x bar dot dot of t plus v, plus v prime of x bar of t dt. All right, so all I did was I rearranged, I just put this term and this term into the same integral, and I took eta of t to be outside. All right, so this, I'm just going to write it again, this all has to be 0. And here's the amazing thing. This has to be 0, once again, this has been following us around the whole time, for any eta of t, as long as eta of t1 is 0 and eta of t2 is 0. But we knew that already. But it has to be true for any eta of t, right? And this is really like the final cool step. So how can this whole integral right here, be 0 for any eta of t? Well, let's look at this thing in brackets, right? This thing in brackets. Well, let me use a different color. I don't know. Does this work? This thing in brackets, right? We're just going to call this something for now. We're not even going to really look at it. This is just something. So, this whole integral is only equal to 0 if this something is equal to 0. And why is that? Well, let's say that there were some t. Say that, suppose there was a t, a value of a time, such that our something wasn't equal to 0. So say that at some time this something wasn't equal to 0, right? Well, if we think about a graph of time between t1 and t2, and like say that, well, I guess I already labeled t, but say that this were the t, where this were that t, where our something wasn't 0, we could just choose, we could just make up an eta of t to specifically catch it right when it wasn't 0. We could just make eta of t a little bump that would catch it right when it wasn't 0. So then therefore, this integral wouldn't be equal to 0. Having said that, we know the integral is 0. Therefore, this something does have to equal 0. All right, so now I am going to just clear away all of this stuff. Just going to clear it all away. I'm just going to look at the something that we now know has to be equal to 0. Whoops. It feels really good to just clear this all away like this. So, this is equal to 0. Now, another way we might write this is as m, and then what's x bar dot dot? Well, x bar dot dot, I can just even write that as a. It's just the acceleration, because it's the second time derivative of our position. So that's ma. And you probably see where this is going. Let's take this term to the other side. Equals negative well, let me write it a little bit differently. Negative dv dx. And as I hope you remember, negative of the derivative of v, where v is our potential energy, negative the derivative of v is equal to F. So just rearranging this a bit, we have F equals ma. Boom! Okay, so by now I have totally proven that for a particle in one dimension with some potential energy, with any potential energy v of x, the principle of least action is the same as F equals ma. But you might be wondering, like, well, okay, all right, if you have a potential energy, then, your force is equal to dv over dx. But what if you have a non-conservative force, like friction? Friction you can't express like this. Well, then what? Well, yeah, that's true. I can't express friction like this. But friction is an emergent force, right? Like, if you could really look at like a table with like all the extremely large numbers of particles in it, and you like rub your hand against it or whatever, and there's some friction, right? Then if you could really take a microscope and look, very closely at all the atoms jiggling and stuff, it would actually be made up of conservative forces. So it's true that we can't accommodate for friction, but in a more fundamental sense, we can accommodate for friction. I mean, we've only done this for one particle in one dimension. But this is also true for multiple particles. And I'm not going to show that here, but you could also show it for multiple particles in 3 dimensions. It's basically the same thing. I sort of want to think about for a second how, just think very broadly for a second, that the principle of least action is some sort of global property of, all the paths we can take from one time to another time, right? Like we're considering the whole path at once. So it's like a global property of the path. And by global, I mean the whole path. Whereas F equals ma is more of an infinitesimal, is that how you spell it? Way of doing things. So that's really like, okay, you have a particle, it's moving with some velocity, and then there's an acceleration, and then in ADT, your velocity changes from here to here, right? And then your particle goes here, and then some other time, maybe it goes here, maybe it goes here. So you're only looking at what the particle is doing from one moment to another, right? You're not looking at the whole path at the same time. The difference is, in the principle of least action, we're saying we know where a particle starts and where a particle ends. But we don't know how fast it's going initially, right? Whereas here, we know where a particle starts and how fast it's going initially, and then we figure out like what path it might take. So there's no, even though you're thinking about things differently and you're phrasing the problem differently, it's only really a difference in how you think about it, right? Because if you want to find your path that goes from here at T1 to here at T2, once you find your path, then you say, well, okay, now that I found my path, how fast was the initial velocity of my particle, right? And then, if you were to then go to the F equals ma way of doing things and start your particle off there, traveling with that same velocity, that same initial velocity, it would trace out the same path. So there's sort of 2 different ways of viewing things. Now, having said that, the principle of least action we haven't really found a good way to actually find this path, except for just showing it's the same as F equals ma, right? And that's not actually, that's not maybe so surprising. I mean, at the end of the day, you're still going to have to do the same sort of stuff. But I'm not going to really talk about it too much, but there are a lot of reasons why this is really a good thing to know about. It simplifies a lot of problems, even though there's still no way to really just find the best path automatically. The other thing I want to say is that it's not necessarily that there's just one good path, right? That there's just one best path. So there could be multiple ways. Like, this wouldn't be true for a particle in gravity. But, I mean, you could cook up a potential in which, there are multiple ways that a particle might get from one point to another in the same amount of time. And all of those would satisfy F equals ma. But the important thing is that infinitesimally, they're all minimums of the action. So even if you have multiple paths that locally, and by locally I mean for all nearby paths, minimize the action, then you can still have multiple paths that locally minimize the action. So it's the same thing in like single variable calculus, right? You can have a function and, let me actually draw it. Yeah, you could have a function and there could be multiple minima, right? And actually, one minima could be a lot smaller than the other. But if you're only looking for f prime is equal to 0, right? Well, you'd have to then take the value you find and plug it back in to see which minima really is the smallest. But actually, it turns out that that's not important. So when I said that the particle takes the path of the least action, I was actually lying a little bit, just for simplicity. It's that the particle takes a path that all nearby paths are a bit more. Not that it's the smallest path ever, because there could be a few different paths that locally have the path with the least action. Another thing I want to say is that you might have noticed saying that the derivative of a function is 0 doesn't necessarily mean that it's a minimum, right? If a function is a maximum at a certain point, it also has a derivative of 0, just as if it has a minimum, or it could be neither a minimum nor a maximum, right? But well, it turns out for the action we wrote, they really are minima. But there are cases that you could come up with where they're not minima. So it should really be called, and sometimes you see this, the principle of a stationary action. And by stationary, I mean that the action doesn't change to the first order when we change the path of it. So stationary, not like a piece of paper, no, but stationary just means that our delta of s is equal to 0. It doesn't necessarily mean it's a minima. It could be a maximum too, although not in the case we had. And it could also be neither a minima or a maximum. So yeah, that's the principle of least action. I'm also going to make a video where I do it in a more general case, and I show you the Euler-Lagrange equation. But it's basically the same as what I did here. It's just a bit more general than the case I did here. All right, so I hope that was exciting, and I hope you learned something about the principle of least action, or maybe I should say the principle of stationary action.